a confirmation that that's started. I'll bring up the slide presentation. Okay, I'm currently recording, and so what I'm going to do is I'm going to try to share my screen. Okay, so would somebody please confirm that you can hear my voice and see my title page?
This is Jay West. I can see your title page and hear your voice.
Good deal. Thank you, Jay. So welcome to the Process Failure Modes and Effects Analysis, PFMEA webinar number 105. Today's March 16th. A couple of really quick housekeeping things. This is the fifth in a series of manufacturing and quality related seminars and webinars. It's a 1 hour, it's really 50 minutes, followed by 10 minutes of questions if you have questions. And if you don't have any questions, we'll end the seminar then. The seminar is being recorded, the webinar is being recorded, and it will be stored, it'll be posted and stored on my website, which is the email address on the title page that you're seeing right now, and that's www.lewisdfm.com. And so I urge you to go there to see them. I apologize that the process flow diagram webinar has not been posted yet, but I had a lot of problems with Microsoft 365 because they've changed the way that they store recorded videos and recorded meetings. So I just was able to obtain the recorded copy of last month's webinar, so I'm going to post it in this month's, probably in the next couple of days. So, and one last bit of housekeeping. While you're at the website, please don't forget that there are course evaluations for this webinar on the website. So just go to the upper right corner and click on course evaluations, and it should walk you through where you have to go to complete one. So your feedback is very welcome. I really rely on that, and looking forward to getting some feedback from you. Okay, so
hey Mike, good afternoon.
Yes.
This is Dale Easley. How you doing, Mike?
Oh, I'm good. How are you, Dale?
Good. Hey, I just want to make a quick announcement if you don't mind.
No, go ahead.
Hey, just a reminder to the group that I sent out, I do a lot of logistics for the group as far as getting the emails out, the meeting makers out. Please be cognizant of that. What Mike has done is put classes together for us, which is very good for just about all the DoD or whoever wants to take it. Anything dealing with content or the subject matter, Mike is the person that you want to call or contact. But all means, I always will send out an email saying if you didn't receive the meeting maker, please give me a call or send me an email back so you guys we can have everything that everyone could be in place for Mike's meeting or Mike's training. So please, by all means, refrain from trying to send him a lot of emails about meeting makers or what time the meetings are. I'll set that up for you so he wouldn't have to have extra work to do. If you can't reach me, Goldie gets the same thing that I do. So keep that in mind and be conscious of that, okay? I do appreciate it. Over. Thanks, Mike.
You're welcome, Dale. Have a good afternoon.
You do the same.
Thanks. All right, so this is the title slide. We got 50 minutes, really not even quite that now. We have a lot of stuff to cover, and I'm going to try to do it without going too fast. If you have any questions, we welcome those. Please submit them as chats. Carolyn is online too with the company. She's my wife, and she's watching for chats. And if you don't feel comfortable doing that or don't have capability, you can wait till the end of the webinar and we start to address questions, and you can always ask the question. Just, open up your mic and we'll go from there. All right, process failure modes and effects analysis is a really big, broad subject, and there's a lot of stuff involved in it. And so it's easily, there's absolutely no way that we can cover all the things in 50 minutes. So what I did is I decided to just cover a couple of the high notes and then to look at an application example. And lots of times we can learn and pick up a whole lot more from an application example than we can talking about bulletized lists. So that's what we're going to do. So we have a couple of lists, some diagrams, and then we'll get into application.
Mike, I don't have it up on my screen.
Okay, can you see people coming in?
Yeah, but I can't see your presentation.
Okay. Well, we have confirmation that people are able to see this, so I'm going to go ahead and go, and we'll work through your problems
Okay.
later. So this is slide 2. The process failure modes and effects analysis that we lovingly call PFMEA provides a structured risk-based methodology for analyzing and preventing failures in manufacturing and assembly processes. This is only...
Sorry, Mike.
Yes?
The slide presentation has gone away.
Okay. I will do what I need to do to bring it back.
I told you it's not showing up.
All right. Let's see. Okay. I have slide 2 being shown. Does everyone see that?
Yeah.
Good deal. Carolyn, can you see that?
Yeah.
Okay, then let's go ahead and get started. So a PFMEA is directly manufacturing and process related. We have other kinds of FMEAs, and we'll talk about that in a few minutes, but this is a process and manufacturing related only FMEA. And so we need to get you familiar with the FMEA process and then apply it uniquely to processes. So the PFMEA is a process design risk analysis tool, and it's something that it should be performed continuously from conceptual design through development. And so we've got some additional PFMEAs that we're going to relate to here in just a minute. But before I leave this page, I want to leave you with the takeaway at the bottom, and that is that the majority of the stuff that's in this PFMEA presentation is coming directly out of Mill Handbook 896A. It's an excellent source, an excellent primer on PFMEAs, and I want to steer you in that direction. There's lots of other commercial books out there and different people that that perform PFMEAs. So there's lots of source material out there for you. Types of FMEAs. You can see right here that we're talking about process FMEAs, but it's not the only kind of FMEA. We do FMEAs at a concept level. We even do them at a design level. And what we're doing today is a process-related FMEA, which is down here. Now you can see there are other FMEAs. There's software FMEAs, maintenance FMEAs, quality FMEAs, and test FMEAs. And that's all well and good. And they all follow the same basic template of trying to figure out failure modes in each of these areas before they actually happen and do something about them. So it's proactive action instead of reactive action. And so once we understand how process FMEAs work, we probably know 80–90% and understand how the other types of FMEAs operate as well. And it's no coincidence that the arrows that are identified on this graphic are two-directional, which means we are taking things out of a design FMEA that affect process and some of the process things that we do that could affect the design. So we're always interchanging ideas and information back and forth from the different FMEAs on a program to make sure that nothing falls into the cracks. And when we find something that's related to something outside of our FMEA, that it gets incorporated into the program FMEA, whichever one is applicable. So what are the objectives of the PFMEA? Well, we have a couple of them here. Identify the potential failure modes of a process and effects of those failures before they occur. Rank some risk probability and consequence associated with failure modes. And we'll be talking about a risk probability number, an RPN, and how to develop that, how to apply it, how to measure it and calculate it. And the third, develop actions that will mitigate and eliminate the probability and or consequence of potential failures. What are the benefits of applying a PFMEA? I've got a lot of them. There are more than I can put on this page. It's a really smart thing, good thing to do, but we're going to go through these one at a time. Conducting a PFMEA early in the manufacturing process development permits early problem resolution of process-related, manufacturing-related issues. PFMEA focuses on prevention rather than detection. Prevention, not detection. That's why I keep saying it's proactive. Thorough application of PFMEA identifies and mitigates foreseeable catastrophic and or safety related failures. So we're making sure that we don't have any kind of safety related or catastrophic failures in the process and in functional use. Okay, I want to keep driving that point home. We are not looking only at process issues. We're looking at functional safety related issues as well. We have that responsibility to do that. By reducing failure points and thereby increasing process quality, costs, production, operational, and maintenance should be reduced. If we look ahead and do this proactively, we should have less problems and fewer costs related to failures on down the line in the manufacturing and quality process. The PFMEA can be tailored or structured to focus on preventing defects most relevant to safety and mission performance, whether they're critical safety items or key characteristics. Key characteristics and critical safety items will probably get more attention in the PFMEA ratings and the PFMEA activity to make sure that we really focus in on those, because we know there's more payback and there's more savings that are going to come from that, along with ensuring mission safety and mission critical activities. So reducing the cost of rework and scrap and non-conforming products, that's another one of the benefits. Increased quality due to a more thoroughly engineered manufacturing process. That's always a good thing. And this is a documented process that's going to help us do that. The PFMEA exposes manufacturing process weaknesses, risks, costs, impact to quality, impact to reliability, impact to serviceability, impact to inspection, impact to a lot of different things. And ultimately, it's going to improve customer satisfaction, because a better product is going to be designed, a better product is going to be produced and inspected. Okay, so how are PFMEAs linked to other FMEAs? And we already talked about them a little bit. We start with a concept FMEA, and then we go to a design FMEA and a process FMEA. So these are different FMEAs. They're run by different people with different criteria, but they're all required to look at the same thing, and that's the system, the subsystem, and the component level. And in the process FMEA, we further divide it into assembly and manufacturing, and then system, subsystem, and component level. And again, as we find things and we address things, those things that we see could have an impact or a failure path in design or even in functionality, we are obligated to share it and pass it along and mitigate that risk using the PFMEA process. Some tips for performing the PFMEA: initiate it as soon as possible. I already mentioned that. I'm not going to repeat that. It's extremely important. PFMEA should be updated whenever there's a new process, a modification to an existing process, or a change in process environment, location, application, training, facility, people. There's a lot of things. It's really very broad, and we'll see that in an upcoming slide. Utilize computerized PFMEA worksheets to collect applicable data in support of PFMEA meetings, actions, and decisions. And that's something that's really important because it creates a paper trail of the thought process that we went through. What did we look at? What did we think about? How did we rate the probability of a failure, or a probability of occurrence, or there are a number of things that we rate and compare. So it's easiest to do as a computer sheet. You can easily do it in Excel. I haven't created one yet, but there are lots of them out there, and they are tailorable, and that's a good thing. But computerized worksheets are a great thing. I urge you to do them. You use them as a guide, and you use them as a scorecard and to help in decision making. So very important. We can't really dive into the PFMEA process until we take a quick look at the fishbone diagram, which is also called an Ashikawa diagram, or the cause and effect diagram. And what we have in this graphic is, on the left, we have all the causes, and on the right, we have the effect or the problem that results from these causes. And this is a real simplistic way of saying, okay, we know what our problem is. What is the cause of our problem? And we start out at a high level, and we identify anywhere from 6 to 10 high level categories of things that our causes could be contained in and could be coming from. They could be, in this instance, we only have 6. We have equipment, process, people, materials, environment, and management. And these are the big primary causes. And then within those, for example, in materials, in addition to materials being a primary environment, we may have a secondary cause that could be that the material may not be cut to the right size, or the material might not be the right material, or it could have scale on it when it wasn't supposed to have scale on it, and now it causes a non-scheduled process operation. So there are some secondary and tertiary causes that can be brought out in each of these areas. For example, another example is environment. If we're required to inspect our parts in 68 degrees Fahrenheit, and they're being produced in a 100-degree environment in the shop, and then we put them in inspection to soak for a day and bring them down to 68 degrees, we have a real big problem. That could be the cause of the problem we have. So these areas are just the beginning point. We have to then do a deeper dive into some potential causes, and we write them on this fishbone diagram like this. This has some very similar ones in machine, method, material, measurement, medium, and then I like this one, man, mind, power, or man, woman, mind, power. It doesn't matter. It's human mind power there. And so it includes things like fatigue and training and, that kind of stuff. So here is a fishbone diagram that has a problem that says 12% of the product fails inspection for screw alignment. What could the potential problems be? And we have some. Tools are worn, instructions could be unclear, screws were the wrong size, encasements were warped. And we start to identify these things, and this is the very first step. It's identifying the effect and then some potential causes. Now, I don't want to get too far ahead of ourselves because these steps are embedded in the PFMEA process, the full-blown PFMEA process. which we're going to move to right now. And so here is the PFMEA process. There are 10 steps. We're going to go through these one at a time. They are process function, determine failure mode, look at failure effects, assess severity, and here is where we're going to rate some stuff, causes of failure. We're going to assess occurrence, and we're going to do some calculation and figuring there. Current process control, and then assess detection. Again, we're going to do a scoring there. Calculate a risk priority number from numbers 4, 6, and 8. This, and this get calculated into that. And then we come up with recommended actions where we kind of go around the horn again here and redo this after we've made some recommendations and made some changes and do a recalculation of the risk priority number of our causes. So let's move on to each one of these things. I'm going to walk you through each one of these, and to begin with, this is a graphic that you're going to see not only here on this page, but in about 40 minutes, 30 or 40 minutes, we're going to take a look at that, maybe even less than that. And right now we want to focus on the top part of the graphic, and you see these circles with the numbers in them. Those are the steps. And what we're going to do is we're going to go from left to right, and we're going to go through and discuss each one of these things. Not on this page. This is the page where we apply them and we start to measure things. But before we can run, we have to walk. And in walking, we're going to learn these things, understand them, and then we're going to apply it to an example to really get the full benefit of how do we really make this work and how these topics in the top come together and are interrelated. So let's get started with them. Here's the steps again. And here's process function. And process function is really what is the manufacturing process. And it can be polishing, deburring, drilling, assembling, bolting, torquing. It can be whatever the manufacturing process is, even inspection. Because in many instances, we include inspection in the process FMEA. In many instances, inspection does not have its own FMEA. Now, what do I recommend? Yes, I do recommend the inspection organization has their own FMEA because that's their expertise, their area of expertise and knowledge. And if we don't do a separate inspection FMEA, it should be a combined process and inspection FMEA. So that's my opinion for what it's worth. But essentially, the process function is a description of the manufacturing process as it's stated on the shop floor process sheet. Okay, we don't need to get real fancy. We relay and restate the process function. Number two, as we went across the top of that graphic from left to right, and I'm hoping and figuring all of you already have those slides that have that graphic in it so you can refer to it. The second one is potential failure mode. And the potential failure mode is nothing more than what are the ways the process or the part can fail. Okay, now I'm going to circle this again because it's really important. We can't just look at only the process, including inspection. We also need to look at the part itself. So what we're looking at isn't just things that are directly related to processes, but that are also directly related to the function of the part. If we do something that is going to affect the final part function and performance, we need to know it, and we need to know it now, because we may be doing something in that part process that's causing it to fail. And if we are, it may never pose a problem in the further downstream processes, but if it causes problems with the part performance, we have to intervene. And so we're looking not only at processing issues, but also part performance issues. Okay, that's why, again, we have them both in here. Okay, examples include bent, cracked, handling damage, hole off location. These are things that could happen. And when you look at a complicated part, there's never going to be any shortage of things that could happen during the manufacturing process that we're going to look at. Failure effects are basically what are the product and process consequences of the component failure or the process failure. Okay. And again, I'm trying to drive home the point that the operation, function, or status of the global manufacturing is what we're trying to do. All right. So if it cannot assemble, if it damages equipment, if it causes excessive tool wear, if it endangers the operator, if it's a safety issue, anything that we think is an issue, that the team thinks is an issue, we need to address. So I haven't really gotten into the team part of it, and I don't have a lot of information on the team approach, but PFMEAs are done not in a vacuum and not by one person. They're done with a group, a small group of people who are knowledgeable about the product, knowledgeable about the process and the techniques in the factory. And so, you know, we need to have the right people. And this is a team activity. Okay. So I'm moving on to severity. And severity is step 4, and it's one of those process steps that we're going to rate. And so severity is nothing more than the numerical rank from 1 to 10 of severity of the impact of the failure. Okay. If the severity of the failure is very low severity, we get a small number. If it's a high severity, if it's a critical safety item, if it's something that is very important, it's been identified as a key characteristic, the severity may be and will probably be fairly high. Because if it's real important aspect or characteristic, that means if it fails, it's going to have more repercussions than something that's a low severity. So you can see now is our first opportunity that we rate the severity. And it's really a subjective numerical rank. So what's a subjective numerical rank? It means Mike Lewis's, determination of the severity of this process potentially being severe is Mike Lewis's opinion. If I have 5 people on my team and we all have a discussion about what's the agreed upon severity of this issue that we're looking at, a potential failure, we need to come to an agreement. And if 2 of us think it's a 10 and 2 of us think it's an 8, then we compromise and we have to come to an agreement. So we try to remove some of the subjectivity and opinions from creating that rank and make it more objective, so that there's some rationale and there's some data that drives the selection of the severity number. Is this a potential problem? Yes, it is. It can cause differences of opinions and arguing, and it can cause delay in making progress in a PFMEA activity or event. But you've got to be able to learn how to do that. And I've got a couple of severity recommendations in the backup that we'll get to that will help you. Okay. So we need to agree on this ranking. It includes minor, major, marginal, critical, and catastrophic impacts in severity. So those are the things you'll see in the little cheat sheet in the back of the presentation. So I'm moving on to causes. This is a description of the cause of the failure. Okay, now we've identified the failures, and then after we've identified the failures, we have to look at what the potential causes of the failure modes are. Okay, and we write them down, we document them, Examples include inaccurate gauging could have been a failure mode. I'm sorry, could be a cause. A worn locator could be a cause. Improper heat treating could be a cause. Inadequate lubrication, inadequate operator training could be a cause. We really don't know, so we're trying to identify the causes of the failure mode we have identified. Okay? And we write them down. We also utilize that fishbone diagram. Remember the cause and effect? Okay, so we know the effect. Now we're working on the causes. And this is where we apply a fishbone diagram to help us to do that. And then we keep going to step number 6, which is the occurrence. Occurrence is the probability that a specific failure mode will happen. Okay? And it's a numerical rank of the probability from 1 to 10 that a specific failure will happen. And again, we need to pick a number from 1 to 10. A low number means it's a low occurrence. A high number means it's a potentially high occurrence. That means it more than likely is going to happen. Okay, so why do we do these things? We want to figure out what are the most important things, key characteristics, critical safety items, critical items that are critical characteristics that are most important, that have the greatest impact and the highest occurrence of occurring. And those are going to stand out. And you'll see that in a few minutes. So again, we need to do this objectively and not subjective. And so it's going to take some time to come to an agreement on this, but you need to come to a scoring on the occurrence. And you will see how that happens when we apply it. Next, step number 7, we look at current process controls. This is a description of the existing controls that either prevent or detect potential failure modes. These are controls that are already in place. Okay? It's to say we're already doing some prevention. Let's build on it from there and let's understand what we're doing, because we may be able to alter what we're doing to affect the potential cause that has been identified. Or these existing controls were done on the first wave when there were issues that were discovered or projected as far as defects. Now, these also come from previous work, because many times companies will be producing a part and they've had it in production for a couple of years. And when we do that, we have a record of all of the defects on those parts. And if they went to MRB, Material Review Board, which was a couple of months ago, we did a webinar on it, there should be proper corrective action that made sure this defect was prevented from ever happening again. So if you have these at your discretion, you are really obligated to go and dig into them and learn from your past mistakes, learn from previous defects and issues. Okay, so the thing we're doing with this step is looking at existing controls that are already in your process. The next one is we then have to look at detection. And this is a little confusing because we have to score detection, and we're not really scoring detection, we're really scoring non-detection. And what do we mean by this? Okay, so let's look at this right here. Detection is the probability that a failure will not be detected. So when we stop and think about what detection is, it is how easy or how hard is it to detect this issue, okay? This potential failure, this defect. And we look at the probability of being able to detect it, or in this case, if we looked at low, which is a low scoring of 1, it's a low probability of non-detection. Okay, that means it's easy to detect. If it's a 10, it's a high probability of non-detection. That means it's really difficult to detect. Okay, I didn't make these up. This is the way PFMEAs and FMEAs in general are structured and they're set up. Just understand you need to get the scoring right. Okay, I've tried to repeat this throughout this explanation. So the numerical rank of probability is a rank of non-detection. Okay, and so that's what we need to know. Then what we do is we create a risk priority number, and a risk priority number is the product of severity times occurrence times detection for each potential failure mode. And here's the formula right here. The product means we're multiplying these things together. We're multiplying severity, occurrence, and detection into this formula to get the RPN number. It's really pretty straightforward. And then after we've scored everything, then we stand back and we say, okay, now we know which ones should be worked on first because they're the ones with the highest RPN numbers. Okay. And then we work to the lowest RPN numbers. Okay. Because the highest RPN numbers are going to have the biggest cost savings, payback, the hardest to find with the greatest impact. Okay. And that's what we want to know. And rather than just throw stones at stuff and argue, we've scored to make it easier to find the highest risk priority numbers. And once we find them, we take recommended action that says, well, what can we do to the process to fix the potential issue or to make sure the part doesn't fail when it gets out into the field? What can we do? What should we do? And then we record those recommendations. Okay. And it takes us back to our worksheet. Now we have already looked at everything on the top. Let's look at the application of each of these things. So what we're doing, we're going to start right here. Operation 70 is an operation number 70 for a front door left hand on an automobile. Operation 70 is the manual application of wax inside the door. And in essence, it covers the inside door and lower surfaces with wax to a specification thickness. Okay, that's the process. That's what we are required to do. What's the potential failure mode? Well, the potential failure mode is insufficient wax coverage over the specified surface.
That's everybody's favorite YouTuber, Trey, would say. This is
Okay, could everybody please go on mute?
a dead cat.
Insufficient wax coverage over the specified surface is the potential failure mode. Okay, so I got somebody else that's talking in the background. Hang on a minute.
Hey, Kevin, go on mute, please. Kevin.
Thank you. I think well, we'll see if it's not too late. I started the process of interrupting things. Yeah, I already started the process. All right, I'm going to have to reshare. Thank you. Hang on just a minute. Okay, does everyone see that we're back on the sample PFMEA worksheet?
Yep, looks good.
Good, thank you
Yes,
for the
sir.
confirmation. Okay, so we already talked about this, already talked about that. We're moving on to right here, number 3, potential effects of the failure. Okay, so some potential effects of this failure is or are, it allows the integrity breach of the inner door panel. It means the corroded interior door panel gets rusted, gets corroded, and deteriorates the life of the door, leading to unsatisfactory appearance due to rust through the paint over time, and an impaired function of the interior door hardware that's in the door. So this is the potential failure, all right? The potential effects of one failure, okay? And so with that, we have identified all of the effects of what happens with having insufficient wax coverage inside the door. So what's the severity of this? And if you look at the top here, you'll see SEV-I. That's the severity scoring of the initial pass of looking at this, okay? And the reason that it's I, it separates and segregates the severity rating of the initial pass to the severity rating of the resultant pass. Okay, so that's why it's SEV for severity I. Okay, so the team has decided through discussion and a little bit of argument that it gets a 7. Okay, that's a pretty darn important issue. Okay, the failure is pretty severe. It's not a 10. No one's life is going to end and the car is not going to crash, which would be a 9 or a 10, but it's still pretty darn important, deemed to be a 7. And that's what we have to have. Then we move on to block 5, where we have potential causes of the failure. And this comes out of the wishbone, or not wishbone, the fishbone diagram. Sorry about that. Didn't mean to make it a little funny there. These are the potential causes. And the one is manually inserted spray head is not inserted far enough. And so really what we're finding out is it's really up to the operator to insert the spray head for the application of wax inside the door and make a determination when the sprayer head is pushed in all the way and how thick the coating is and when it got started and when it, they can't see a whole lot, but it's manually inserted. Then the other cause of the failure, this is just one cause. There's a potential another one. The spray head got clogged. If the viscosity is it too high, is the temperature too low, the pressure too low, it could be a sprayer head issue. And the spray head could be damaged due to operator bumping it or dropping it, so we could have 3 potentially different things leading to this. But then in order to move forward here, we have to rate the occurrence of each of these 3 potential causes. And if we look at this, we do that in the occurrence rating. And we look at trying to answer the question, what's the score of the manually inserted spray head not being inserted enough? What's the probability of occurrence? Well, without a lot of help given to the operator to know when enough is enough, as far as inserting it, it's been determined by the team it's a pretty high occurrence level. Okay, that means it could happen often. The sprayer head getting clogged would happen less. Carolyn, there are people in the lobby. Can you let them in?
Yeah, just one.
Okay. So it would get a 5 for that rating, okay? And the occurrence rating of 5 is medium, which is probably normal. The sprayer head being deformed due to impact, probably really low occurrence of occurring, so it would get a 2. So you can see that we have 3 potential causes that they now have different occurrence ratings. Then we move on to the current process controls for prevention. And we say there are already some things, that are being done. A test spray pattern at startup and after idle periods. And this is already being done. So is this. We're doing preventative maintenance program to maintain the head. Maybe we don't do it enough. Maybe we should do it more often. But this is what's currently being done. So before we recommend something, we need to know what we're doing. And this is what we're doing. Then we move on to step 8, where we look at the current process control and some recommendations. I'm sorry, not recommendations, some things that we can do for detection. Okay. And that's why it's current process controls from a detection standpoint. And right now, we are doing a visual check every hour. One shift for film thickness, including a depth meter and a visual for coverage. We're also doing a visual check after or each hour, one per shift, for film thickness, depth meter, and coverage. Okay, so we're already doing some things from a prevention and a detection standpoint, and these are the things. Because what we'll need to do if we want to make some progress and some improvements is we want to do something more. Now, we're measuring these things from a detection standpoint, and they all get about a 5. They're all about the same. And so what that does is it gives us enough information to create our RPN number. And the RPN number for manually inserting the head not being inserted far enough is 280. And the RPN number for the sprayer head getting clogged due to viscosity and temperature and pressure is 175. Well, wait a minute, how come it's not 280? Well, because even though they all have a severity index of 7, they have different occurrence numbers of 8, 5, and 2. So that changes the answer, the product. So 280 came from 7 times 8 times 5 equals 280, and so on and so forth. The 70 came from the 5, the 2, and the 7. So now we know what one to focus on if we're only going to focus on one, and it's this one. What's the recommended action? Add a positive depth stop to the sprayer. Automate spraying is another thing. So we've brainstormed and we've collected some information, and we see that we have some recommendations to do. What do we do after we come up with our recommendations? We assign them and make somebody responsible, an organization responsible, and a due date. And then after we do that, we give them time to go do what needed to be done. And then we move on to this column of the actions taken and actual completed date. So what occurred was they actually added a stop. The sprayer is now checked online with that stock. Now the automated spraying approach was rejected due to the complexity of different doors on the same line. So this one got killed, but this one moved on. And after we add that to the process, we rescore the severity, the rate of occurrence, and the detectability, and we got new scores. Severity is still a 7. Occurrence went from an 8 to a 2, and detecting stayed at 5. But we now have an RPN score, a resultant RPN score of 70, which is a fraction of what our original RPN score was before we went and did something. So this, ladies and gentlemen, is in a nutshell, is a practical application of what is involved in conducting a PFMEA study and how to capture it, how to record it, and how to utilize it in a computerized data sheet. Okay, some lessons learned that I want to touch on are, and there's quite a few, many of them are very common sense oriented. Untimely application of PFMEAs. That means it was done after the design and processes were locked in, which is never the right place. insufficient recognition of failures and causes. We didn't do a deep enough dive into the failure modes and causes. And you got to do that. Failure to identify the customer. Who is the customer? Is the customer the next process operation, or is it the ultimate customer in another state? So we need to know who the customer is and what they require and what they need, because it's just as bad if that customer is the next process operation and we screw up what is needed to properly do that process. And so there's an argument there in who the end customer is. And so that's not always done appropriately. Too narrow in the scope of analyses. Multiple failures, degraded conditions, and downstream effects really need to be explored. Weak recommendations. Improper failure classification. Too optimistic, not consistent. You got to have recommendations that are actionable. You can't use operator error as a failure mode. You got to have something better, deeper, more detailed than that. And then, of course, ignoring existing system data that we already talked about from previous production information and rejections and nonconformances. So those are the lessons learned. And that is my last slide. But before I take questions, I want to show you that we have a recommended severity criteria and rankings in backup, and occurrence criteria and rankings, or the probability of failure and possible failure rates that lead to potential rankings, and it may help you not argue as much. So with that, I'm going to open the discussion up for questions, if there are any. Carolyn, do you have any chat questions? Okay, there are no chat questions. Are there any from anyone in the audience? Okay, don't forget, you're all on mute. Okay, well, I'm hoping that if any of you have questions, you get a chance to review the slide presentation that was sent out to you in advance. And if you have any further questions from what I lectured, feel free to go to the website that I shared with you at the beginning, www.lewisdfm.com, and you can watch this webinar again. And you can always email me a question if you want to. So.
Hey, Mike.
Oh, yes.
There appears to be a question. Somebody can't come off mute.
Okay. Can you relay the question?
You want to type that in? Can detection ever be approved?
When you say, okay, so can detection ever be approved? Detection is really, we're not approving or disapproving detection.
Sorry, typo. Improved.
Oh, improved. Yeah, so detection is, detection needs to be a part of the recommended actions and that need to be taken. Because as we as a team are working together to try to figure out not just what's wrong or what could go wrong, but how could we fix that, we have to understand that the severity and the ratings for occurrence, severity, and detection are something that come into the equation for, can we improve those things? And if we can improve the detectability of the potential defect, then we have in essence lowered the detection score of that new process. Okay, so the answer is, of course, yes, you can. And so it isn't what can we do to modify the process that makes it more detectable. It's what can we do to the detection process to make it more detectable. Okay, so I'm hoping that that answered the question there. Any other questions? Okay, thank you all again for your attention.
Hey, Mike.
And oh, yes.
Oh, I'm sorry, this is Dale. Just a quick question for you. I know I wasn't there in the beginning of your slide deck,
Yes,
but I did have one question that maybe that a lot of us can benefit from.
sure.
One of your first slides you had on there types of FMEAs. You had at least about 5 or 6 of them there. Based on your experience, can you tell us as a group where we should actually, looking at the acquisition cycle, where should we actually engage each one of the FMEAs? Over.
Okay, yeah, sure. So my knowledge, my experience in FMEAs is a lot of these FMEAs are to be done as early as possible. Okay, I mean the short answer is as early as possible. I'm sorry, that's not a real good answer, but let me look at each one of these things. And before you can do anything in a process FMEA, you have to sit down and do a concept FMEA, a functional concept FMEA. What do we want this weapon system to do? How high, how fast, how long, how good, how bad, what kind of accuracy rate, what kind of failure rate. You need to know a lot of things. And the more we start to know, the more we put on paper, we're at the very early design portion of the product. As we start to do that, it's never too early to start working on a concept FMEA, okay? And as we do that, we have to understand that unknowingly, many, many times, we're locking in the design approach as well. And so that's why when you do product design properly, you get different people involved from design, from quality, from test, from maintenance, from software. It isn't just because you're eventually going to have to do a FMEA. It's because that makes sense because that's where you need that input. But you can't go off and do a FMEA, the software, until we nail down the concept, or we even nail down part of the design and start to figure out what kind of software requirements are going to be required. And so it's an ongoing thing. And if I could make a recommendation, it's to insert yourself into the process of the concept FMEA, the design FMEA, and any of the other FMEAs, the software maintenance and process quality and test FMEAs, and make yourself, inject yourself, whether you do it yourself or you have somebody from DCMA do it. You need to be a part of that process, because only when you're a part of that process can you say, you know what, it looks to me like we're advancing far enough in selecting manufacturing processes that we need to be doing a process FMEA before we go any further. Okay. And so that's part of the challenge. So the second answer to your question, Dale, is I went through the big saddle blanket chart. Okay, I think that's what you guys call it, the acquisition roadmap. And I looked for concept FMEA, design FMEA, process FMEA. Those things aren't there. I couldn't find them, and I'm not sure why they're not there. It could be because it's really hard to put a nail into where exactly it should start and it should occur. But it's got to be, there's the right time for it. And we have to inject ourselves in that process to know when the right time is. Now, the other thing too is it can be a part of the contract schedule, the program master schedule. I mean, if it was up to me, if I was representing the government, I would make the customer put these milestones in the program schedule, along with all the risk milestones and all the other things that the contractor doesn't normally want to do because it ties them down. These are the things that should be integrated into that program milestone schedule that gets used to manage the program from day one contract award through delivery. And these should be in there. Why they're not from the documents I looked at, I don't know, but I think they should be. They are so powerful. They can do so many different things. You get the right people together and you can solve all kinds of problems and save time, money, and effort in creating better products that are safer, last longer, and are just overall better. So, Dale, I hope I answered your question.
Yes, you did. Thank you.
Okay, are there any other questions? Okay, thank you all for your attention, and I look forward to the webinar next month. We're working on the subject matter right now, and I'll send invitations to Dale, who will send them off to you all as soon as we figure that out. So thank you all. Bye.
Thanks, Mike.
Sure.
Thanks, Mike.
I have to stop the recording, Carolyn.